Hello, today we are going to start Unit 3, which is going to be about graphing different types of functions. So today we are just going to do kind of an introduction onto all the different functions we will be using today. So we call these parent functions. There are several types of functions, including linear, exponential, quadratic, absolute value, and a lot more. Each of these different functions could be considered a family. And in that family, they will have unique characteristics that will be shared among their family members. So, a parent function is going to be the most basic function that is used to create more complicated functions. So, we're going to look at a few different types. Okay, the first one is one you've already seen before. It's just a line. This is what we call a linear function. So a linear function is just going to be a straight line. And then we're going to talk about some key features with each of these, focusing mostly on domain and range. So if you remember back to when you first learned about domain and range, domain is your x values. So what x values is your graph using? You can kind of think about it if like you were walking along the x-axis. If you looked up or down, is there going to be some graph there? So like we see this graph is going forever to the left because this is going to continue on, and it's also going up forever to the right. So we would say this domain is going to negative infinity, which is over here to the left, to positive infinity to the right. It's just going forever from left to right. And then range is the same idea, but we're thinking of the y-axis now. So is this graph going down and up? How far down and how far up is it going? So this graph is going to keep going down forever until negative infinity, and it's going to keep going up until positive infinity. So our range is negative infinity to positive infinity. And this notation that we're using right here is what we call interval notation. So interval notation will use either parentheses or square brackets. We use a parenthesis when we can't actually touch the point. In this case, since it's going to infinity, remember infinity is not an actual number, it's an idea or a concept, so we can't actually ever get to infinity. So since we can't get to it or touch infinity, we're going to use parentheses. So I'm just going to write a little note here. Down on the bottom, we use parentheses. That means the graph can touch it or include that specific number. So includes or touches. And I was an idiot and I wrote that backwards. Brackets, so the little square brackets, that is when the graph includes or touches. And parentheses are where you can't actually touch it or include it. So like in the case of infinity, can't actually get to infinity, so we can't ever touch it, so we don't include it and we put parentheses around it. Versus like on a different one where we might actually be able to touch the number, we put a bracket. So if you wrote that down that backwards, I'm sorry I wrote that the wrong way. So this is how we will write our domain and range when we get to our problems. We'll be using either brackets or parentheses depending on if it touches or doesn't touch. We'll also talk about intercepts. These should hopefully be familiar to you. X-intercepts are where we cross the x-axis, so we see we're crossing at 0. Y-intercepts are the same idea, just where do you cross the y-axis? It's also crossing at 0. And then here's a few other things that we're not going to focus on today, but we will later in the unit. We're going to talk about when it's increasing versus decreasing, where it's positive versus negative, if it has max and mins. And then we're also going to look at something called symmetry. We're going to do this one today. So symmetry is going to be if the graph is symmetrical, and there's actually going to be a couple different types of symmetry. So I'm going to come up here and write it in this blank spot. So when we have our symmetry, we can be symmetrical around the y-axis, and we can be symmetrical around the origin. So we call these even and odd symmetry. So even symmetry is where it is going to be symmetrical around the y-axis. And odd functions are going to be symmetrical around the origin. And what that means is that if you can flip your graph upside down or like turn it around, it will look the same upside down as it does right side up. So for example, on this one, we have the straight line here. This is an odd one because if I take this graph, so if I like put my finger down and I spin my graph upside down, my line looks the exact same as it did before. So it's symmetrical around the origin because we can spin it 180 degrees and it looks the same. So that's going to be odd, or think of that as being around the origin. And then ones that have even symmetry are going to be ones that look like this next one. Here's a graph of a quadratic function or a parabola. You've heard them called that before. See how like I could fold it in half over that y-axis. So that one is going to be called an even symmetry. And then if we look at the domain for this one, this parabola is going to keep going up and to the left for forever. So even though it's steep, it's going to still be going to the left for forever. And it's going up to the right, so it's going right forever. It will take a long time to get out to infinity, but it is going to the right to infinity. So our domain would be negative infinity to infinity. So again, think of the domain as your x's, and the range is going to be as your y's. So my parabola, it doesn't use any of the negative y values. It's just starting right at 0, and it is going up for forever. So we are going to say our range is from 0 to infinity. And notice that this one does have a bracket on it, and that's because we're actually touching 0. I can actually get to that number. But again, with infinity, we can't actually ever get to infinity, so we use a parenthesis on infinities. So that will be our range. And then again, today we're not going to focus too much on these next few ones. We'll get to that later in the unit. But then the symmetry is even. So today we're just focusing on domain, range, and symmetry. So again, that's a quadratic function, makes that kind of parabola or U shape. Okay, the next one, this is called an absolute value function. So remember, an absolute value is those little straight lines. And what an absolute value does is it turns anything negative positive. So like if I took the absolute value of -2, it would turn to +2. So that's why we get kind of this V shape, is we take all of these positive numbers, and as soon as my line would start going negative, it's going to flip it back up. Kind of think of flipping it into the positive section, so we get that V shape. So absolute values make a V shape. Again, we could shift them around up and down or left or right, but the parent function for the absolute value is going to just start at 0, 0, and then it just goes up with the slope of 1 in both directions. So if we think of the domain for this shape, it is going to the left for forever, and it's going to the right for forever. So our domain would be negative infinity to positive infinity with parentheses. And then the range, again, we're not using any of these negative values. So I'm not using any negatives, but then it starts at 0. And then as I keep going up my y-axis, it's going to go forever. So our range is going to be 0 to infinity, but because I can touch 0, I'm going to use that bracket. And then we can't actually touch infinity, so we use a parenthesis. And we're going to skip these few for today and go down to our symmetry. We see that it can reflect across that y-axis. We have that kind of mirror shape there where it just flips over, so this one would be even. Okay, so that is the absolute value function. Got a couple more. The next one we're going to look at is the cubic function. So a cubic function gives kind of this little, I don't know if you'd call it like an S shape maybe. We get kind of a little squiggle here. That's going to be for x cubed, anything that has an x cubed in it. So for this one, if we are going along our x-axis, it is going down, but it's also going to the left for forever. It's going to keep going out to the left. And it's also going to go up, but it's going to keep going to the right for forever. So our domain is negative infinity to positive infinity, again with parentheses. And then same with our range. This is going down for forever, and we're going up for forever. So our range is negative infinity to positive infinity. And then if we think of the symmetry on this one, this graph is going to be another one that's symmetrical around the origin, because if I think of turning it or rotating it, I can even literally flip my paper upside down, my graph looks the exact same. So if it can rotate and spin around the origin and look the exact same, then it's going to be that odd symmetry, or it flips around the origin. Okay, let's look at the square root function. So that's going to happen when you have the square root of x. So this one is kind of almost like a little half of a parabola. So it's only starting at 0 and it's bending and then kind of flattening out. If you remember, squares and square roots are opposites of each other. So if we think of our quadratic function, our parabola, the opposite of that is a square root, x squared and square root of x. If I think of turning this on the side, we get kind of that same shape as we do with the square root function. The only thing that's missing is that bottom half. And the reason we don't have that bottom half is because we can't actually take square roots of negative numbers. And we also wouldn't be able to pass the vertical line test. We can't have, if I draw a vertical line, I can't cross 2 times in my graph. So what we do is we just take that top half of that little sideways parabola. And this one does go on forever to the right, but it stops at 0. I don't ever go into my negatives on my x-axis. So if we look at our domain, so far all of them have been negative infinity to positive infinity. This one's only going to be from 0 to infinity. And again, because we can actually touch that point, we're going to use a bracket on 0, but a parenthesis around infinity. And then same going vertical, I'm not using any of my negatives because again, we can't take a square root of a negative. So I'm starting at 0, and this is going to keep going up forever. It's going really slow. It's not a very steep slope, but it is still going up. So my range is going from 0 to infinity with a bracket and a parenthesis. And then if we skip down to symmetry, this one doesn't have any. I can't flip it over the y-axis. And if I turn it upside down, my graph's going the other direction. It's not up here where it should be if it was supposed to be symmetrical around the origin. So sometimes you will have ones that aren't symmetrical. So this one would be one of those cases where you don't have any symmetry. Okay, so that's a square root, but let's look at a cube root. Remember, cube root of x will have that little 3 in the little nook there. A cube root of x is going to look almost like a square root function, but it bends back the other way. So cube roots are the opposite of cubics. So our shape is almost the same, right? We have this kind of cubic shape, but it's flipped onto its side. So with cubics and cube roots, you can take the cube root of negative. So that's why we're able to come backwards here. We can't take square roots of negatives, but we can take cube roots of negatives. So the domain for this one, it's going to keep going to the left for forever, and it's going to keep going to the right for forever. And so that gives us a domain of negative infinity to positive infinity. And then range, it is still going down. It's going really slow, but it is going down, and it is going up really slow for forever. So negative infinity to positive infinity again. And then the symmetry on this one is also going to be odd, just like the cubic was. If I think of spinning it upside down, it's going to look the exact same shape. So that's always a really good trick to tell if it is an odd symmetry. Okay, the next one is called an exponential function. You might have seen this little guy a little bit last year, but that's where we have e to the power of x. E is not just a variable. Here, e is like a number, kind of like pi. And so we have this exponential function. You'll see e's happen a lot in things that have to do like in nature. So we'll get to a whole unit where we use exponentials later on this year. But anything with e to the power of x is going to grow exponentially. That's where that phrase comes from. An exponential function starts off slow, and then all of a sudden it spikes up really fast. So if we think about this as of the year 2020 that we're in right now, think of the COVID cases. It started out pretty small, and then more people got sick, and then it grew exponentially where a lot of people are sick. Or I always joke it's kind of like bunnies. You have 2 bunnies, and all of a sudden you have 12 bunnies, all of a sudden you have 30, and all of a sudden you have 400 bunnies because they breed exponentially fast. So here's your exponential function. If we're going left to right, this graph keeps going forever to the left, and it keeps going up to the right. So there is a little bit of it going up and right. So it will be from negative infinity to positive infinity. But then for our range, we're not using anything negative. So this graph right here skims along the x-axis, but it never actually crosses the x-axis to go into negatives. So it's going to go from 0 to infinity. And notice we don't have a bracket on this one, it's a parenthesis. That's because we have what we call an asymptote right along this x-axis, where the graph's not actually going to touch 0 or touch the x-axis. It's just going to kind of skim right along it without ever really touching it. So that's why we don't have a bracket on here, we just have a parenthesis. And then on this one, same as symmetry, we can't fold it in half. If I spin this upside down, it's not going to match up, so we have no symmetry on this one. So that is your exponential. So what we're going to do now is we're going to look at some different graphs. A few of these we didn't look at today, so we'll just cross them out. But we're going to try and identify what the parent function is, and then what the symmetry is for that. So if we have all of our little graphs out with your notes, hopefully you have them printed off or you wrote them down, you can refer back to them. Okay, so on this first one, we have this graph right here, and it is going up and kind of bending to the right. So if we look at our graphs, this one is related to an exponential. This one is going to be a log function. So logarithms, remember exponentials, they come along the base and then bend up to the top. Notice how they're kind of mirror reflections of each other. They reflect across that diagonal line. So exponentials, this would be e to the x, and this is going to be log of x. So logarithms, we're going to spend a whole unit on logarithms and exponentials. They are backwards of exponentials, so they start really steep. So we're almost vertical here, and then it's going to slow down to where it's almost fat, or not fat, flat. So symmetry on this one, we can't rotate it, we can't mirror it, so there's none on this one. Okay, this is another one I don't want to spend too much time on because you like really never see them or use them. This is a step function, and you can probably see why it's called a step function because it kind of looks like little stairs. This one does have symmetry around the origin, because if I took this and spinned it upside down, it's just going to look like stairs again. So this one is odd, or you could think of that as being around the origin. Okay, here's this next graph. Hopefully you can recognize it from our list that we went through. So it's coming and curving and then going the other direction. This one is the cube root of x. So cube root function. And this one is going to be odd again as well. If I took this and spinned it upside down, it will flip around the origin. Okay, hopefully you recognize this guy. This one is a quadratic. Again, quadratics are your x squareds. So this one is going to be an even symmetry, or think about it as flipping across the y-axis. So I could fold it over the y-axis. Okay, this next one, this wasn't on our list of ones that we were looking at a second ago, but this actually has to do with the last unit we just did. These are going to be rationals. So rationals, we're going to spend more time graphing these as well, but they have what we kind of call like a saddle shape. So there's going to be an asymptote right here. Our graph is kind of skimming along the x-axis and then comes down, and then it skims along the y-axis without ever touching or crossing it. And then it flips to the other side of the y-axis, skims along it, and then bends to skim along the top of the x-axis. So rationals, they do change and they can have more than one asymptote, but again, this is just the parent function. So it has an asymptote at 0, 0, or the y-axis, and an asymptote at the x-axis. And these, again, if you remember back to our rationals, they are going to be ones that have an x down in the denominator. So 1 over x would be the case for that one. This would be, again, the parent function. It's the easiest rational we can do. It's just an x in the bottom and a 1 on the top. But again, the parent's the simple one. We can complicate it and make it a little bit trickier. So the ones that we just dealt with in Unit 2, they would be considered like the children of this parent function, and they will be more complicated. But this one does have symmetry because we could spin it. So this one is an odd symmetry, or think about being around the origin. Okay, next one, we have this little shape here. Again, it's really similar to this shape, but this one's going along the x-axis, where this one is centered more along the y. So those can kind of help you to recognize them because they're going to be opposites of each other. That was the cube root. This is going to be x cubed or cubic. So your cubic functions, they're coming and they bend, and it's almost like you have like a half of a parabola going down and half of a parabola going up. This one's going to be another odd one. I could take this graph and spin it. Okay. We're going to skip this one. We're going to spend a whole unit on these guys later on. So just skip that one for now. Okay, let's go to this one. Hopefully this one's easy for you guys. Just got a straight line, so this one has to be linear. So remember, linear functions are just an x. And it is going to be, I could rotate it and spin it and it will look the same. So this one's an odd symmetry. Okay, the next one looks like just a little half of a parabola. This one is going to be your square root function. So remember, we can't take negatives of square roots. So that's why we don't have the bottom half of that square root or parabola shape. We just have that positive top half. And this one has no symmetry, so I'm just going to write none. Okay, we're also going to skip this one. These ones that we're skipping are your different trig graphs. We're going to spend a whole unit graphing trig functions, so we're going to not take the time today. Okay, this one is just a flat line. Notice that there's no slope at all. I'm not going up to the left or down. It's just totally flat. So it would be easy to confuse this as a linear one, but linears have to have some kind of slope. This is what we just call a constant. So the constant is just going to be a number that it's going through. And if I look, it's going through 1, 2. So our equation would just be x equals 2. We just have a number going straight through at 2. And there's not going to be, well, I mean, I guess you could kind of think as that as being an even one. You could flip it in half across the y-axis. Okay, here we have two parts of a graph again. Notice that we have an asymptote. This graph is getting close to the y-axis but never touches it, and then it skips to the other side and never touches. So these ones are, again, your rationals. There's different kinds of rationals, but they are going to have those asymptotes in them. And then this one, it looks like it can flip across that y-axis, so it's going to be an even shape. Here's another trig one. We're just going to skip that. Again, we're going to spend a whole unit doing those little funny looking graphs. Okay, we've got a nice V shape here. Can you guys remember which one that is that makes the V shape? This one is your absolute values. So that's where you have the little absolute value lines. And this one, again, you can mirror image it across the y-axis. Okay, and then our last one, notice this one is starting off really slow and then it's growing really fast. Can you guys think of which one that one is? This one is the exponential. So these are your little e to the x ones. And this one has no symmetry, so I'm going to write none. Okay, so that's hopefully kind of just a review of identifying different graphs now that you kind of know what the parent functions are. So in your homework, it's going to be really similar where they will give you like pictures of graphs and you just have to identify which parent function it goes to. So I would have like your notes out until you can memorize them. So you remember this is linear, we have a quadratic, we have a absolute value. Some of the questions will have to do with domain and range. So remember, domains have to do with your x values going side to side. Range has to do with your y's going up to down. And then there will be some that have with the symmetry. So they will ask you, can you flip it across the y-axis? Can you rotate it around the origin? Maybe there is no symmetry. And then just remember, when you are doing the domain and range, you will need to write in that interval notation like this, where you're using either parentheses or brackets. And remember, brackets mean you touch that point. You actually can get to that point and touch it. Whereas the parentheses means you can't touch it. And so whenever it's going out for forever, like it's going to infinity, we can't actually get to infinity. It's not a number, so we never actually can get there, so it can't touch it, so we use those parentheses. So hopefully that feels clear and you can understand how to do that. But that's what your homework is going to look like. So go ahead and make sure you have all these different parent functions kind of written down. And again, today we're just focusing on domain, range, and symmetry, and we'll look at some of this other stuff later on in the unit, but just those main 3 things today. But if you guys have any questions, as always, feel free to reach out to me. Just email me. We can set up a Zoom call or something like that, and I can help you out. Hope you guys have a good day. See you later.